Let's tackle a relative motion problem. Here's sort of a standard problem. A river is 20 meters wide, has a current, the water moving at 3 meters per second south relative to the ground. A swimmer jumps in, the swimmer starts swimming at 4 meters per second east relative to the water. I'm curious to know how long it's going to take the swimmer to get across the river and what the swimmer's velocity relative to the ground is. We're going to keep things kind of boring to start. Since it says the velocity of the water is 3 meters per second south, that tells me that the riverbanks, kind of a boring river, the riverbanks are also north-south, and the water in there is moving south at a rate of 3. That means someone standing on the ground, if they looked at the water, they'd see the water trickling by at 3 meters per second. If there was a bit of garbage floating in the water, someone on the ground would see that garbage drifting straight south at a rate of 3 meters per second. The swimmer jumps into the water. It's almost as if they didn't realize there's a current. They point their nose straight east. They jump in, point their nose straight east, and start swimming at 4 meters per second. Someone on the ground is going to see something slightly different. They're moving forward at 4 meters every second, but they're also drifting south at 3 meters every second. The resulting speed is what we get when we add those two velocities. I haven't dealt with the 20 meters yet. It doesn't show up on our triangle because it's not a velocity. The 20 meters tells us how wide the river is. We can actually deal with the 20 meters right off the bat. One of the questions is, how many seconds does it take the swimmer to cross the river? I know that the river is 20 meters wide. From logic, no real math, I'm told that every single second the swimmer's in the water, they move 4 meters per second towards the other side of the river. Every second they're in the water, they go 4 forward and 3 down. 4 forward, 3 down, etc. So just kind of by little logic, not having to really do any real math, or we could do the math. We know V equals D over T. If they're moving forward at a rate of 4 meters per second, and they've got 20 meters to go, we can do a quick little math or logic. We can see that it's going to take them 5 seconds to cross. What's key about this is we can only use velocities and displacements that are pointing in the same direction. 20 meters was the distance straight across the river. 4 meters per second was the velocity pointing straight across the river. To finish this one off, we can do a little bit of Pythagorean theorem to figure out how fast the person's actually going as seen from the ground. V squared equals 3 squared plus 4 squared. This, of course, you probably saw it coming, is a 3, 4, 5 triangle. We're not quite done. That tells us how fast, but velocity requires a direction. Let's call that angle x. If we look at the triangle, we know the opposite and the adjacent. That's a tan function. Within rounding, we'll get that the angle is roughly 37 degrees. So putting it all together, the velocity of the swimmer, as seen from the ground, is 5 meters per second. They were pointed straight east, but the current pushed them 37 degrees towards the south. It would look a little bit funny from the ground. The nose or the head of the swimmer is going to be pointing straight east, but they're going to be drifting on that 37-degree angle a little bit towards the south.